Join us on a voyage through the wormhole, your gateway to groundbreaking thinking on AI, space exploration, a healthy planet, and a more intelligent future. I'm your host, Jonathan Knowles.
The Wormhole is produced by Trillium Technologies, leading the application of artificial intelligence for planetary stewardship, space exploration, and human health. Help us explore what's over the event horizon by following us on LinkedIn and Twitter at trillium.tech. Together, let's build an intelligent future.
Hello and welcome to the Wormhole. Thank you for joining us again. We have another fascinating guest to spend some time with today, and we're very happy that you have decided to take time out of your day to do that. Before we get started with that very special guest, as always, we want to introduce you to one of our FDL community members. These are researchers and faculty and partners from a variety of science domains and AI domains and technology domains. So please, let's get to meet one of our community members today. Hello, and welcome to this special edition of Wormhole, 5 Minutes with an FDL community member. And today, we are fortunate to spend a few minutes with Hannah Rudasser. Hannah, it is so nice to have you here. And this is all about getting to know you and your research. So let's get started right away and tell us a little bit about how you ended up a scientist. When was it in your life that you decided that's what you wanted to do? And specifically, how did you end up in the domain you're in today?
So, thanks a lot for having me here. I think I first got into space physics during an internship during my undergrads. And there I worked on the Qt data simulator. And I really realized how fascinating the field of space physics is. So afterwards I did my master's degree in theoretical and computational physics at the University of Graz. And here I really developed an interest in AI. So afterwards I decided to do my master thesis at the No Center in Graz, which is a research center for big data and AI. And my master thesis was on automatic ICME detection. It then resulted in a first author publication, but I also got to meet my current supervisor, Dr. Christian Mössl, who then offered me a PhD position. So currently I'm a second-year PhD student at the Austrian Space Weather Office, and here I'm lucky enough to really focus on combining physical models with AI, which I think is really interesting.
Why do you think that's interesting, Hannah?
Well, I think it's really cool because, of course, we have a lot of data. We gather data all the time, and the more data we have, the more we need advanced methods to really make use of them. But at the same time, we're also increasing the knowledge that we have about physics. So I think using hybrid models is really the goal.
Great. And when you think about the work you've done at FDL, what would you consider to be the most meaningful thing that you have been a part of? And what do you believe the most meaningful outcomes of your research are likely to be, or that you hope to be?
Yes, so our group was focusing on improving solar flare and CME forecasting, which in itself is a really important topic because especially nowadays where we're really dependent on technology, it's super important to also know what's going on in space weather. So during the project, what we did is we designed a very modular framework that is able to facilitate the use of data from different instruments and missions, such as, for example, SDO, stereo, solar orbiter, all of that to serve as a proxy for the visual mission. So I think our framework really will be very useful when new data arises from new missions. But I think I'm personally even more excited about the work that we did in the background. So during the project, we realized that unfortunately, the current state of the art of solar flare forecasting is still really limited. So some machine learning models, even if they get good scores and the numbers look great, when really looking at the results, they often struggle to outperform persistence models. So models that predict that the current conditions will remain exactly the same. And when realizing this, we put a lot of effort into thinking about how we can construct better labels and get more meaningful results from machine learning in flare forecasting. And I think I'm most excited about the fact that we really got to address these issues, which I think will be really important moving forward and getting new data.
Wonderful. Thank you. And finally, where do you think you're going to be in 10 years, 20 years time from now? What would you love to be working on when we think about that amazing future?
Well, 20 years from now, we will have gathered a lot of data from the first Vigil mission and the second one, hopefully as well. So I'm really excited to see how we made use of more data. And yeah, speaking now, I think I'm excited to stay where I am and continue making use of data and physics.
Wonderful. Hannah, thank you so much. It's been great to learn a little bit about you and what you're working on and how you ended up here. We appreciate your time today. Thanks.
Thank you.
Fabulous. We hope that you'll take an interest in our researchers and the incredible research that they've been doing, as well as our partners and our faculty members. And you can learn more about them and their work by visiting fdl.ai and esa.ai. Well, let's get into it with our guest today. I'd like to bring him up to the stage if we could right now. This is my friend, my colleague, Bruno Fromont. Bruno and I have had the privilege to become colleagues working with we'll just say a blue chip Fortune 100 company that's working on and tasked with some of the most meaningful work I've certainly ever done. And it's just been a pleasure to get to know you. Bruno, thank you for joining us here today, my friend. It's good to see your face.
Yeah, thank you, Jonathan. Glad to be here.
You know, first of all, I didn't know to ask you about this, what I'm first going to ask you about, until we started chatting about you doing the wormhole. And I'm very interested in knowing what your connection to the Himalayas is. And apparently you're a mountaineer. I had no idea. Tell us just a little bit about mountaineering and wow, the Himalayas. Go big or go home, as they say, right?
Right. So I guess it's an early attraction to the heights or of some sort. But I was born and raised near at the border of Switzerland, in near Geneva, in France, but close to Switzerland. And very early on, my cousins would take me to the mountains, and I developed kindness for the mountains, and of course I have an appetite for and a great curiosity to explore, and which will lead us to I think an interesting conversation on science exploration. But I try to explore the world physically first, and my father was a journalist, and I developed some interest for other countries, other places in the world, on the planet, and combining the two early on, I didn't want to live, a limited life. I think this was a Steve Jobs quote: "Don't live a limited life." At 20 years old, I went into and went in a trip to China when it was still a very difficult country to access. I went up, in the Himalayas then, and then I went back, a couple of times. Took a lot of pictures, climbed some mountains, and I gave me a lot of perspective on life and other cultures. So that was an early fascination for again unknown parts of the world.
I can't wait to talk to you more about your experiences there. That said, today we are very interested in talking to you about satellites. You, of course, are the CTO at Intelsat, a company that was created in 1962. One of the oldest satellite companies. I guess technically, a year before that, AT&T launched a satellite, but I don't know that I'd call them a satellite company in the same way that Intelsat is one. So truly the oldest, I'll say it today, the oldest satellite company around, and operating the largest fleet of satellites in the world today in multiple orbits. I'd love to hear a little bit about how you ended up in space, and what was it about space that attracted you, and how did you end up at Intelsat? What was your journey to get where you are today?
Yeah, thank you. Of course, yeah, these the meandering that lead to a certain position, sometimes take a lot of detours, and but for me, and back to that early childhood, and my curiosity for science, actually even literature, everything um, was leading me actually first and foremost into the world of computers. My, I was living in a town that was very close to CERN, the physics, research center where that, has, a number of particle accelerators. And I was like, when I was some time off, I would go and tinker. And I had the privilege in the 70s to be able to access computers, which were not really, prevalent in those days. And and then at the time I was reading Scientific American, there was an article about a program developed by Terry Winograd, from MIT, called Shudlu, I think. It was basically a natural language interface, manipulating blocks, in a hypothetical world. And I was so fascinated by what a computer could lead you to. Of course, now we're in this age of AI and ML, but at the time I was like, oh wow, this is mind blowing. I want to do this. And that was one aspect of my curiosity for computers, and then morphed into AI research in the future, later on. But the other thing that happened in early 70s for me was I was reading the newspaper from and there was published first page, the first images from Voyager, 2 and 1. For a kid in those days, I mean, I was just blown away. And that's interesting too. I want to do that too. So one thing led to the other. I started to do some research in AI, but then came back and worked in the European space industry, trying to combine early on AI and satellites. I was offered a position at Thales at the time, to do automated diagnosis of what could go wrong on a satellite, and developed, keen interest for the field. And then, worked on my way, up in the company. And at some point, because of my travels, I wanted to do something different. My kids were born, and then I said, well, I want to go back, if not to MIT, somewhere in the US. And I got an opportunity at Intelsat, and I applied, and I just loved it. And so I stayed there for now more than 20 years.
Wonderful. Wow. Well, let's do this. Let's do a bit of a satellite 101 for people.
Right.
I think that that might be useful for us to just very quickly talk a little bit about low Earth orbit, medium Earth orbit, and geosynchronous. I've been reading some geospatial news this morning. Some geosynchronous orbit, a little bit about what that means, and perhaps a little bit about the different kinds of things that happen in different orbits. We're certainly familiar with communications satellites, but these days we're very interested in Earth observation satellites, and beyond just typical optical cameras, all the other kinds of things that we can do, because there's a whole host of things we can learn beyond having an optical camera orbiting. But let's start with what LEO, MEO, and GEO are, and about the different kinds of satellites that are up there these days.
Yeah, sure. Very, the orbits, refer to the geo orbit. That maybe we can start there, because this is where the first, Intelsat satellite called Early Bird was launched, and I think a whole fleet of satellites thereafter from Intelsat and others. This is basically an orbit that is at 22,000 miles from the Earth, 36,000 kilometers, and it has the peculiarity of the objects in that orbit fall exactly at the same speed as the Earth rotates, and basically the satellites appear to an observer on the Earth as if they are stationary, even though they are moving pretty fast. And so there's only one geo orbit around the Earth, around the equator. It's pretty high, of course. The signal takes some time to go to travel to that place, but of course, it has enormous advantage in the sense that once you are up there in that position at a particular longitude, you can absolutely stay over that area and serve from a bird's eye view, multiple continents. Actually, there was a famous paper from Arthur C. Clarke early on that actually described the possibility of putting 3 satellites at equidistance around that orbit, and that would create basically a global coverage of the planet. We still have the paper from Arthur C. Clarke in our hall here at Intelsat, and is a kind of a godfather for the company. Using this principle, Intelsat developed a fleet and a standard of communication over the years. And of course, in those days, in the 60s, that was the first and primary way to communicate across continents, beyond the cables. The cables were not as developed as they were today. So that's a bit of an history lesson on how the GEO came to be. Of course, at the same time, for military reasons, people would launch, things in the low Earth orbit to begin to listen, to some, to communications around the world. So from that point of view, I mean, you can go down and there's a MEO, but I'm going to skip right to the LEO orbit. Of course, if you want to decrease the latency of the signal, in other words, to have a quick response as your signal bounce back from the Earth to the satellites and back again to the Earth, the lower you are, the better. The issue is if you are lower on the Earth, the coverage, you're not talking about covering continents, you're covering smaller area, and you need far more satellites to cover the planet. So to establish a global coverage, and these satellites keep moving, so you need to have a so-called constellation of satellites in the thousands, maybe, to basically to provide the same coverage as a GEO satellite constellation would provide.
This is what we're seeing with, for instance, Starlink satellites.
That's right. Starlink is,
just for everyone's reference, it's about 90 minutes per orbit when you're in LEO, correct?
Yeah, that's right.
And Starlink's a good example of having to have a lot to have the kind of coverage that you might want.
Yeah, I would say if you're in GEO, I would say 3 satellites theoretically can cover the globe. Thousands are required to cover the globe with the same level of coverage, in LEO. And in the middle, you have maybe a Goldilocks orbit, MEO, which is not very developed, except it's very famous for the GPS system. But there are other satellites. It's less populated, but it's maybe the not too hot, not too cold type of compromise between different attributes. But let's say, if we stay in LEO, it requires a lot of investment because as you can imagine, everything you want to change on that system, you need to replicate 1,000 times for the next generation. At the same time, you have resiliency in numbers. A single satellite death will not compromise the system, so that's an advantage. At the same time, because of the cost, the satellites are usually much smaller, less capable, on an individual basis, and requires some compromise. Whereas in GEO, you're talking about multi-tons type of satellites, huge payload in tens of kilowatts, a very different value proposition. And in MEO, maybe that's an intermediate orbit, not very developed, but the European company SES has developed a system called Empower in that orbit, and there will be others. So that's basically for the orbital dynamics of these orbits, if you will.
Nice. And one of the things that we work on in the FDL Helio Lab, that's FDL-X, which is a NASA funded program. We think a lot about this because we think about in heliophysics the role the sun plays on thermospheric expansion, which is one of the downsides of LEO that you have to pay attention to. Because as we know, orbit is, as you said earlier, falling. And if you're hitting more little bits of things as you fall, you will slow down. And if you slow down too much, you will burn up. And so we do have some incredible research at FDLX around predicting thermospheric expansion in order to deal with that and all the other things that one might have to think about. So it's not just a safe and easy place. I guess that's the reason I'm bringing this up there. There's things we have to pay attention to. And I certainly, as a user, want them paid attention to. I have a Starlink. I have the Starlink Mini that allows me to, as long as I'm driving at less than 100 miles an hour, get about 200 megabits per second internet anywhere on the globe.
Yeah.
So I care about being able to keep those things up there. That does make me think a little bit about this notion of space sustainability. 6,000 Starlink satellites alone, let alone all the other things that are in LEO here. GEO, a lot less crowded. MEO, at potential new developed space. You mentioned SES earlier. I should say Intelsat and SES are in the process and have been for a while now of merging together, which will significantly increase the number of satellites operated by this new company created through this merger. What kind of things should we be thinking about when it comes to sustainability and keeping track of all these? You guys operate a lot of satellites from your ground stations around the world.
Right.
How do we deal with that? How should we be thinking about that?
I would say it's a new problem that has been studied theoretically for years, but only now do we see the potential impact coming to be potentially realized in terms of, because of the number of objects that are around the Earth, as you said, Jonathan. And the problem with space is, even though you talked about the drag in lower orbit, still object can float and orbit for a very long time before decaying, depending on where they are, which is
whether operational or not. By the way, you used the word impact.
Yes.
I liked the double entendre use of that word.
That's right. I think we have developed and it's obviously a global problem. The institution that regulates space. I mean, there were treaties drafted in the 60s. Right now, we are very active at Intelsat with other operators, including SpaceX, to try to understand what this means, what should be the guidelines, basically, to operate in space. You don't want to turn space into a junkyard. And that could be very difficult to operate, and then you would destroy this environment, which would be bad. But also from an economic perspective, it would be very risky for future investments and sustainability. Right now, we are leading. We have one of my guys is president of the Space Data Association. We try to manage all this debris. We work with JSPOC, the government entities, to track what's floating out there. Just to give you a sense, there are about 33,000 objects in the catalog that are of size greater than 10 centimeter, like from very small or dead satellites or parts of satellites in all these different orbits we just talked about. That's staggering. So we even if we're in GEO, which is arguably less crowded than LEO, we still manage every day some potential conjunctions with debris, right? So it's automated, of course, and so far it's very manageable. But like I would say, 10 to 20 a day. That's not nothing. And people are afraid, of course, of what would become something uncontrollable. I mean, Kessler described a phenomenon a while back in a famous paper that says, hey, you could trigger the current of a nuclear reaction. By this, I mean, a debris would hit a satellite that would then explode, then create more debris, and it would then eat more satellite, and this would quickly become out of control, and we don't want to reach that point. So first and foremost, understand the data, manage the data out there using government and private sensors. The second aspect is, can we act in space to take care of this? Not only being good citizen, apply rules in terms of deorbiting the satellites, which we do, of course, after when they become too risky or unmanageable. Let's make sure we deorbit before they're becoming uncontrollable. And then can we develop, robots, or service models in space to go and take care of the garbage, basically, and sustain the life of these satellites, in a good way. We have developed an Intelsat, some collaboration with Northrop Grumman, where we have sent, and we were the first to dock, a robot to an existing geo satellite in space, and then bring back fuel to the satellite to make sure, the life would be extended. And we know a number of companies we're working with that are working on actually cleaning up, basically going and grabbing big, dangerous objects that are inactive today, and send them, in outer space, basically, or graveyard orbits. So this is an entire ecosystem that is being developed in, I would say, the past 5 years, and hopefully with, data, means to act upon the environment, hopefully things will be under control for the foreseeable future.
And I imagine that, well, I know that the number of satellites, if we just look at the last 5 years as a data point, has changed dramatically, beyond exponentially, as far as the number of things up there. So if this has been evolving for the last 5 years and that number has been increasing, this has got to be an intense game of catch up to or at least an intense effort to try to stay just ahead of just what a mess it could be, because it could be truly devastating.
Yes, and of course we talked a lot about the debris and the management, all that, and the potential of compromising an orbit. But there's more to it, right? I mean, the as a Earth citizen, you look at the night sky and you see now these satellites floating, and if you are an astronomer, or you want to make sure the sky is also clean. I mean, it begs some question regarding solar reflection on these objects, and the pollution, the optical pollution for astronomers, for NASA, for other research institutes. So we want to make the number of objects less reflective and be under control. That's another important part of it.
Of course. So let's now talk for a minute about the value and why it's so important for us to get this right. So the first satellites were communication satellites that were launched. And of course, some of us are old enough to remember, live from, and that was made possible live from other parts of the world. Starting in about 65 or 67 was the first live from television broadcast. So communications, telephone communications, television communications, radio communications. But more recently, we have seen that satellites have contributed greatly to things such as agriculture and climate monitoring, through things like Earth observation, and of course the intersection of AI and these things. As a matter of fact, Trillium for the ESA created a report called the Earth Systems Predictability Report that I'd encourage people to check out, that starts to talk about the big picture of some of this. But those are just a few of the things: agriculture, climate monitoring, through Earth observation. How do you think those advancements are making a difference today?
Certainly, I think we can observe too. I mean, if I want to project it first, if I want to look at it, today, the number of sensors is also proliferating. I mean, it's because of the advance in telecom satellites and their production and their costs. Access to orbit has been easier than ever, which is good for people that want to experiment and launch, missions, payloads, to basically observe the planet in all different type of wavelength, using different types of instruments. Recently, we launched, something with NASA called Tempo, which is actually monitoring the pollution over continental U.S. and Mexico at a resolution that was not possible before. That's one aspect. The number of sensors, the instruments that were initially also in higher orbits can come closer. There are more and more remote sensors coming to low Earth orbit with a greater resolution, cheaper. But more importantly, what you're going to see is the refresh cycle is going to improve in low Earth orbit, because, of course, having persistence over a particular area will open up new applications, and you did cite a few of those. Some industries are rediscovering or discovering for the first time the power of combining communication and data from space to their own business on the planet, because again, you have a unique perspective from space that allow you to have a global view, to use the data to your advantage, or for the advantage or the benefit of your customers. And certainly, there's another compounding effect to this, and I think you and I had discussed it at some point, which is the fact that not only you have this new Earth observation ecosystem that is developing and bringing benefits to agriculture, automotive, energy sectors, Internet of Things, potentially. The combination of telecommunication satellites and remote sensing to basically create data relays in space to bring the information sooner and faster to the end user is also a synergy that is going to create new information and better models for these industries.
And, when we think about things like disaster response, it's incredibly powerful to think about floods and fires and all the different things that fall into that category. And, we mentioned the word wavelength at least once today, and we've talked about this as well, radio waves. And actually, there's a lot we can learn from radio waves and their use in satellites that we've learned over the years. But we're sort of moving around in the spectrum these days with how we're able to communicate, because you also mentioned latency between GEO and Earth, or GEO and MEO and LEO. And there's some interesting work being done in how we use something other than radio waves to reduce that latency between these things. Talk a little bit about that advancement, if you would.
Yes. I think the notion of using all the spectrum that is available, the electromagnetic spectrum, and create communication channels or ways to carry information from point A to point B is something that's is never going to stop. And there are of course some physical barriers to some of these propagations, but I think over the years they are overcome. Right now, a lot of development has happened, in the domain of optical communications in space. And by the way, if people don't know, the laser communications in space, the signal goes actually, between quotes, faster in space because than in a fiber optic on the ground. It has to do with the medium in which the wavelength is traveling. But yes. With this type of communications using optical links, you have an ability to establish, again, a transport structure in space between objects to combine access to let's say, the International Space Station and relaying satellites, or even in the future to connect. As we explore the space further, connect beyond the Earth and to the Moon and other planets using laser communications. This is enabled in the next generation of the Starlink satellite, actually, and it's not only Starlink, there are others. We have been working on creating this relay system in space, and I think that's going to be again a force multiplier on the capabilities you can develop. I think a lot of the things that are being done on the ground today people talk about in terms of communication a lot about the the cloud infrastructure that has been developed, and people talking about moving the cloud to the edge. Well, I think computing capabilities will also be pushed to the edge, including into space. So having the way to interact with other spacecraft, like in a swarm, if you will, but also compute, events and insights based on the information you receive and route signals, locally, will make for a great advance in the future in that ecosystem.
I can imagine that swarm being in touch via laser with the Blue Origin orbital reef space station,
Right.
these future space stations that will have these kinds of things built into them, and as you say, beyond. In a world where we have literally high school and junior high school students building satellites to be launched. Very quickly, I was not long ago having coffee here in Los Gatos, where you and I just had coffee a week or so ago, with a VC friend of mine who said these words, and it hit me that, wow, this is the world we live in now. He said, oh, look, I bought a ride on a spacecraft, but I can't use it. Do you know somebody who needs to launch a CubeSat-sized thing? And that's astonishing for people of our age to hear those words from somebody, but that's truly the world we're moving into. And as you say, beyond Starlink, the things Intelsat is doing, and Amazon with Project Kuiper has their initiatives. So these things are happening. They're happening so quickly, which makes me want to ask you, the name of this series is the Wormhole interview series. And I like to ask, what can you imagine? And feel free to be a little sci-fi, but maybe that sci-fi that you can truly imagine we could get to with regards to some of this. You might have touched on some of it so far now, but what can you see on the other side of the wormhole that truly excites you?
I think, first and foremost, we are, at a time on the planet where, as a species, we're asking ourselves a lot of questions, right? And you could argue even right now to be, if you look at where we stand, some macro trends around, more, getting more, countries, centric and closing some borders, but actually innovation and space is still, for us as humanity, a new frontier, and it gives us a unique vantage point on and a reflection on what we are and what we do and what our planet looks like, which is why I think this is very important to continue. And I think the whatever happens, the humanity will be drawn to space because that's what we have been doing for hundreds of thousands of years now. And so by that I mean our space system, our solar system will progressively see more traces of our civilization, for better or worse. It's going to happen for sure. I was mentioning the bubbles, and I see in the ecosystem that you don't launch things anymore and you forget. Actually, you go and you maintain this environment. In other words, there is a bit of autonomy and compute power given to space, or these objects that are going to be there and live their life. They are autonomous. When we send robots to Mars, they don't count on us all the time. They fly on their own. Whether they are a small copter or something. So you're going to see a more developed ecosystem, and potentially leading to small factories, small engines of information, potentially mining with asteroids, right? So that will require relays, control, information sharing, risk management, and an entire business is being developed around that. And I think it's going to be for the good of people that want to explore, to go out, but also to go back. The benefits of finding source of energy to protect maybe from solar radiation in the future are going to benefit the planet. You mentioned, the agriculture. Given the climate, trends, really fine tuning how we want to best feed the planet using space vantage point and sensors is going to be benefit for the humanity. So that's what I see, more collaboration actually in space. That's what you need to do because you're really at global scale, and technology that branch out and create autonomy to a number of I would say, space computers and robots and things that are going to, be the factories of the future.
I love it. I can't wait for that future, and I'm honored to be collaborating with you to help make that a real future for future humans. Bruno, thank you so much for being with us today. I'm going to ask one more quick thing of you. What advice do you have, especially when you think about our community of people here at the Frontier Development Lab at FDL? Something that might help them as they are just starting their journeys. Many of our community members, some of them certainly are faculty and partners who've been doing this for a while, but many of them are postdocs. They are just getting started on their career in science, and they come from heliophysics and biology and chemistry and astrophysics and data science and AI, all kinds of domains, but they're just getting started. What's your advice to them?
Simply, first of all, if they are already starting, it means they are curious. They are thirsty for more, for learning. I think they need to keep it that way. Maybe what's specific about space, I think this is, again, I mentioned the new frontier, but I think it's one domain where more than ever, there are people that love to drill down and of course do research in particular, but more than others, maybe technology domains or sciences, in space, you need to collaborate between different domains. So, and this is where innovation happens. It's between AI and space, and physics, or it's between that particular area of engineering. So combining things is going to be very critical. You cannot solve just with one particular science or expertise. These are big system problems that you try to solve in space. So that keeping that openness and curiosity about other branches of science and technology is what allows you to solve problems. And maybe the overall, I think there for people to succeed more, space is still very risky. We talked about all the great progress, but we forget about all the stumbles and the rockets blowing up. But you need to persist and have courage. It's not like a slam dunk, and I can tell you even today when we launch, we've done that 100 times, a satellite on a rocket, and we see, we push the button. You feel it in your body, right? And you have that excitement, that rush of adrenaline when you launch to space, because there is risk. It's not like if there was no risk, it wouldn't be interesting. But so that courage part of your mindset is going to be very important.
Courage, curiosity, persistence, resilience. It's wonderful. Bruno, thank you again for being with us today, my friend. It's just a pleasure to hear from you about this stuff, and certainly look forward to doing more with you. And thank all of you for joining us today. We hope you enjoyed this, and we are looking forward to seeing you all again soon on the next episode of The Wormhole. Thanks very much.